Hi, thank you for joining me. I'm Yuval from MissingLink, and I've been a software engineer for the past 12 years. I had the privilege to work on a variety of projects, including a computer vision blood test for malaria, a game I love called StarCraft, and today on MissingLink, where we build tools that let data scientists focus on the science. And to do that, at MissingLink, we surveyed over 100 AI companies asking about their workflows. With that, we'll explore the current and future of operations in deep learning. So, this story begins with us humans. We're great at inventing, producing, and using tools, and the oldest of which is the hand axe, dated back to 3 million years ago, and we've been improving it ever since. In the 1940s, the first modern computers were built, and in 1984, the first modern operating systems were released. And software around this time would pretty much ship and update once a year. This was such an obvious concept that to release a version once a year that Microsoft called the 1995 version of Windows Windows 95. And the next version was supposed to be called Windows 96, but after some delays, it was called Windows 98 by the time it came out. So the cycle then was maybe even closer to 3 years for a full release. And in 1991, Linux came out and the first public World Wide Web browser. These two pieces of tech define what we call the Internet. And 14 years later, in 2005, the first version of Git was released, the most popular source control system today. In 2009, the term DevOps was coined, and I'll explain what that means in a minute. And in 2016, Netflix reports that they have thousands of daily changes in production, and that these are meaningful software changes being pushed out. Now, at this point, you might be wondering, why is this guy showing us these random events through history? Well, the point I'm trying to make is we went from deploying or releasing software once or a few times a year to releasing software updates to customers thousands of times per day. That's about 1 million times more frequently. And we have to thank two stars for that: the internet, which can transmit software globally and instantly, and DevOps. Hopefully everyone here has heard of the internet, so I'll only explain what DevOps is in a few more slides. Now, first, I want you to know this isn't just a fuzzy feeling I have. For example, in this 2018 report with 30,000 tech professionals surveyed, it turns out that companies that deploy a new change within an hour or less have a 7% chance that that change will have a production failure associated with the change. And companies that take much longer to push out changes, that it takes them months, they'll have about a 50% failure rate for changes. Which, if you take a moment to think about it, it makes no sense. It's faster and more reliable. I'm interested. So, how does this work? How did we get here? Well, in the 90s, developers and operations folks were separate and at odds. Developers were paid to innovate, push new features, to change the system, and that makes it less stable, or just breaks it entirely at times. While operations people, on the other hand, they had the keys to production, the machines and databases running the app. Ops folks were paid to keep the system stable and to make sure nothing ever breaks. And this didn't work out too well because the company as a whole needs a balance between stability and innovation. So in 2009, these worlds combined and a new word was invented: DevOps. To automate everything, including all the tiny and annoying things you have to do when you deploy to production. Do a lot of testing, which must be automated, which is what levels up reliability, and monitoring software so we can detect mistakes when they're made. And you need to version everything so you can backtrack when you detect these mistakes. And at first it might seem like this is adding a lot of work that engineers wouldn't want to do, but the end result is actually a massive leap in quality and productivity. It's through these ideals that companies like Netflix can push out so many updates every day. And in other words, we went from this mindset, where new features are a threat, to this mindset where we can be confident that production is safe and evolving rapidly. But there's this one weird thing. During this conference called DevOps Days, Netflix was given a talk about how they think about DevOps. And they say they don't. So this is at a DevOps conference called DevOps Days. What's going on here? What he later explains is that there's no single person or group at Netflix that does the DevOps. Everyone does the DevOps. So what happened here is that the definition of DevOps also evolved. Initially, when it was coined, it was a term describing a combination of two roles. A role plus another role, that's a role. It even kind of felt like the DevOps people were just ops people. But now we're at the point where we can automate all the grunt work in DevOps so every engineer can self-service and do their own DevOps. It really is a culture. It's something that we all share and do. And my definition of culture is pictures with superimposed text. And as with any culture, there are objections to the culture. And there's explanations defining exactly what each thing is, with animated examples and calls to action, and even disaster response guidelines. Now, I didn't make these pictures. I found them on the internet, so some folks think version control is pretty important if it takes precedence over fire. At least that's my conclusion. And my point is that this DevOps culture thing, maybe in a modern company, there's one group responsible for building or choosing the DevOps tools, but the culture is that it's everyone's responsibility. Every engineer automates their process so anyone can use it. Every engineer writes tests for their own systems. When an engineer deploys a change to production, that same engineer will monitor and check that it's working. I mean, who better to debug a change than the person implementing it? That's why DevOps is a culture, because it's everyone's responsibility. In the end, DevOps for the software developer is this tiny arrow here. How to get your code out there. And we've practically automated everything in that equation. But in the case of deep learning, there's more moving parts. Even though a neural network is a simple idea, a data scientist has to do a whole crap ton of manual work on a day-to-day basis to spin up and set up training machines, copy data over to these machines, copy back the model output, integrate data back from production, not to mention what data scientists are actually supposed to be doing. This is what deep learning is about. It's a linear idea. You start by getting data, you clean it, you tag it, write some code to train a model, test your accuracy or loss, and repeat. This is the science that data scientist wants to focus on. But oftentimes they can't. Let's see an example. Let's say you're a computer vision data scientist, and your team builds an algorithm that figures out which demographics entered a store. Just from the security footage, your app gives a report on age, gender, and how long the client was there. So the product has been tremendously successful, and you have a lot of happy clients. But today, something is different. You notice your boss slowly approaching your desk with a stoic, maybe even sad face. And he says, our clients were looking at the numbers, and they didn't make sense to us. In our contract, it says 90% accuracy, and they're saying it's more like 30%. We might lose this $7 million contract. Can you tell me what happened? How do we fix it? And your natural response is to put on your detective hat. So what happened? Maybe our code had a bug. Which version of the code did we deploy? Who made the changes? Did we test the changes? These are the immediate questions that come to mind when we're talking about code. But there's another piece here. Maybe our model had a bug. Which version of the model did we deploy? Who made the changes and did we test those changes? Or maybe the training data had a bug. Which version of the data did we train on? Who made these changes and did we test them? Maybe even it's something else entirely, like maybe the data in production is just different from what we trained on. So code, models, and data, they're all business critical, and in some cases life and death critical systems. But today most teams only version control and continuously test their code. That's pretty much where we were with software in the 90s. We've learned through decades of blood, sweat, and tears that version control and automation are needed to ship reliable products fast. And that was just one example of a challenge, to look back and investigate a bug. There are a ton of other operational challenges in the deep learning world. Optimizing speed and cost, launching a lot of experiments at once without losing too much hair, modifying the data without invalidating all our existing experiments, and just data manipulation at scale is hard. There are so many challenges that we think deep learning deserves its own ops culture, and we call it DeepOps. Bringing over the best practices from software development into the world of deep learning and AI. Handling operations the right way. So to do that, as I mentioned, we surveyed over 100 AI companies asking about their workflows, their biggest challenges and solutions. So what do these teams do? Let's start from the building blocks, how they interact. At the core of experiments, there's still modifications of code and data, and the models are just the outputs of the code. So our basic building blocks are data, code, and machines. And when we map out what we do with them, it ends up looking like this. A bit of a tangled mess, because we need quite a few tools to do this, and as I said, there are a lot of moving parts. In many ways it can go suboptimal or wrong. But maybe it doesn't have to be this way. I mean, ideally, your code magically runs on strong machines when you need them, and you don't have to worry about trucking your data around, and you can easily reason about your data. Now, note, all these processes still need to happen, but we can automate a lot of them away. And that's what DeepOps is about. Each one of these arrows and ways of automating them away, so they can fade from our lives and we can focus on the science. So let's talk about code. Specifically, how we control, share, and move code around. Luckily, that's kind of done. With code, there's not much to talk about. Everyone uses Git. Thank God that engineers can agree sometimes. Not indentation, file system, or language, but at least for versioning code, Git is pretty much the only way to go. So that's settled. But maybe that's a bit tedious. I mean, I often test a lot of different changes when I'm doing research. You know, another layer here, a hyperparameter there. I'm experimenting. These are experiments. A data scientist could shoot out 10 of these in a minute. It would be a huge hassle to have to commit every single one of these tiny changes. So we don't. We just don't commit. I could work for days or weeks only to commit when I'm done. And the risks from that are obvious. You lose your work history. If you want to map out what you spent time on last week, well, that information's gone. You can't reproduce it in case you notice you had a very good or a very bad experiment you want to try again. And having a note for every experiment would also help the team stay informed and aligned, especially if it's a distributed team. And honestly, seeing a line go up and to the right is fun. And one last whoa moment for me was finding out that data scientists don't stick around that long. So companies want to make it easy for new devs to get up to speed and know what the person who just left was working on. And one solution we saw, that every time you run your Python, you write on a piece of paper why you ran it and what were your results. And this is the answer we got from an AI company. It's focused on AI, and it has over 100 employees. You can imagine it can be hard to share these notes, but this is a solution that real companies actually use. And there are some more serious solutions, actually. For example, the Eclipse editor can save local history, though I personally don't like Eclipse that much, so that doesn't help me. And Dropbox I do use, but the problem with plain file history is that it's kind of hard to reach the different versions on the web interface, and the changes there, they lack context. Why did I make the change, and what was the result of it? And what we do at MissingLink is if you have a file called ML tracking repo, you put a URL for a Git repo in it, and then every time you run your Python code, MissingLink will commit the exact state of your current repo to that tracking repo. So your main repo stays nice and tidy, but every experiment has fully documented code. So there are others who do similar things like CommentML and others. I'll explain what I mean by Lego in a bit, but that's pretty much all I had to say about the code. And with that, it brings us to number one, the data. Often in computer vision, the data, it's just a big folder full of files. Maybe some labels or tags and metadata files sprinkled about. And this works, but poses some challenges. For example, when you're trying out different neural network architectures, you'll want to start by testing with small amounts of data to see if anything's working at all. How do you get just a subset of a folder? Well, the answer is you have another folder and you just copy a few files over. So if you want to use 10% of the files to do a quick test, you create a folder called 10%, drag some files over there, and now if you want to reproduce the experiment or share it with colleagues, well, I hope you didn't delete the folder and then you have a good way to share that gigabyte with them. Another solution is to use a database. This works pretty well for NLP or text-like use cases. A query is a good way to define the data slice you're operating on. But for computer vision, you can't really store images in a database because databases perform poorly with large binary files like images and video. So you still need to move the image files around alongside fiddling with the database. One solution we saw is having a small SQLite database file that's stored with the image files. Though that can get hard to share and merge changes with the team, it's still a pretty good solution. And another problem is, whenever you run your code, it looks at a snapshot of the database at that moment in time. And if you ever modify the database, well, that exact code and query will yield completely different results. So you still can't confidently reproduce experiments and investigate bugs. And there are solutions to that problem, some better than others. Pachyderm and S3 both support versioning data, and MissingLink has a data management system that supports versioning queries as well. There are a lot of players in this space. I'm not going to recommend one over the other today, but I just want you to know that you should be versioning your data, and you can. These data systems support efficiently storing petabytes and beyond. So please, version your data. And how does it all work? Well, through the miracle of content addressable storage. It's a core piece of a lot of these technologies. It's the same algorithm that's used by Git and by the Blizzard Games asset system. It's a brilliant and simple storage scheme, which I'll just say in short, the hash of the content of a file is its file name. So if you change the file contents, well, its file name changes too. So objects in the data store are effectively immutable and versionable. I encourage you to look it up. Next up is the machines. Now, when we ask companies how they manage their machines, we get a variety of answers. Some have a GPU on their desk. Some have them under their desks, or under someone else's desk, even better. Or on the cloud. A lot of companies answer all of the above, because they'll normally use their own GPUs and bust out the cloud when they're overflowing or need a boost. But how do you coordinate these events? Some groups use a spreadsheet to decide on which day who gets the GPU. And one company we spoke with just leaves an AWS GPU instance on forever. So if you want to see if you can use the GPU, you just SSH in and see if anything's running. And if it's already in use, just wait for it to be done. That's $200 to $7,000 a month, which most often isn't even in use. They just didn't want the hassle of spinning a machine up and down, not to mention the man hours wasted waiting for a job to finish. Now, these strategies kind of work when you're one person and in no rush, but they fall apart when there's 3 or more folks fighting over GPU time. So, why did this company hate spinning a machine up and down so much? I kind of get it. I mean, let's spin up a machine on AWS to see why. So, you sign into Amazon, hit the big launch instance button, you pick an operating system, you pick an instance type, scroll all the way down to the ones with the GPU, configure which network it can access so no one but you can access the machine, pick a storage type and size that'll match your dataset needs, add a tag because you're organized and you want to know exactly how much this costs you, and you want an itemized bill split for each specific AI project the company's working on, right? Configure some ports so you can SSH in and copy stuff out, and make sure your SSH key is there so you can log in. And we're in. Then we have to do the same thing we do every night. Try and reduce loss. And I didn't even get into setup and how getting the environment set up and getting the code and data in there. It's a hassle. You don't want to do it often, and I do understand why that group just didn't want to bother with spinning a machine up and down, even though there are ways to automate it, at least parts of it. You can write a script with everything in it that SSHs in, copies in files with SCP, gets the code with Git, gets the data from S3, installs the Docker, launches a container, or you can use Kubernetes to manage your own little cloud that does these multiple times a day, and you could also use Terraform if you want to define your infrastructure in code, which is something I enjoy doing as well. If you feel like that's a lot of work, it is. And what's happening right now in the field of AI is that we're getting a ton of meta tools that combine all these and simplify the workflow dramatically. Because ideally, it's just one click, one line of code, or one command in a terminal. We just want it to be easy so we can focus on this, the science. Getting the best data, building the best models, and measuring our progress as we go. But there's this tension where if you want to make a tool easy to use, you have to remove the knobs. There are many startups that have this Lego-like solution that does everything for you, where you have this black box that you throw data at, and you get a model out. And it works great, but if you want to tweak anything, then you're out of luck. The other end of the spectrum, you can do it all on your own, and you might have a rough time, but you'd have complete control if you go the white box route. So the new AI tools are trying to achieve this balance, to create a magic box solution that's easy to use, gives you sane defaults, but still lets you tweak whatever you need to. And here's a list of tools that are aiming for that magic box that's easy and powerful. In a future session, we plan on diving into these various platforms, what they do well, and how to use them. Now, for quite a few slides, I've just been talking about tools, and I want you to remember that tools are where it starts. But what we actually need is a DeepOps culture. We can deliver better results faster if we all do our part in automating away the kludge, versioning our data, and building systems that make it easier to focus on the science. So with that, I'd like to thank you for your time. Please subscribe to our channels and drop us a note on what you'd like to hear more about next. Cheers.